Hi there, welcome to my channel. In this video, I am going to explain how to implement the binary search tree iterator. Let's look at the problem description. We need to implement the binary search tree iterator class that represents an iterator over the in-order traversal output of the binary search tree. Okay. Basically, we have to implement the constructor and then the hasNext method and the next method. So the root of the binary search tree is passed as the input for the constructor. Basically, this has to initialize the pointer that points to a non-existing element in the binary search tree. And the hasNext function will return true if there exists a number in the traversal to the right of that pointer. Otherwise, it has to return false. And then the next method moves the pointer to the right and returns the number at that pointer. So the first call to the next function should always return the smallest element in the binary search tree. That is the leftmost leaf node. And we can always assume that the next calls will always be valid. That is, there must be at least one next number in the in-order traversal output. Okay. Let's take a look at the example 1. So this binary search tree has 7, 3, 15, 9 and 20. And we are given a sequence of operations that will be performed on this iterator object. So basically, first operation is the creating constructor, which takes the root of the tree. So they just specify the entire tree as an input to this operation. Then the next method, which doesn't take any input, so that's why this is empty. So and then hasNext is also don't take any input, so that's why this is also empty. Basically, this is a sequence of operation and the corresponding input data. Okay. So first, when we create the binary BST iterator object, so we initialize the pointer to a non-existing element, and then the second operations, when the next method is called, the smallest element in the tree, which is 3, is returned. And then the second call to the next method will give us the next smallest element, which is 7 in the binary search tree when we perform the in-order traversal. Okay. And then the fourth operation is hasNext method call, which returns true because there are still some elements in the tree that are not yet traversed. So likewise, there are sequence of operations. Okay. So constraints for this problem is the number of nodes in the tree is in the range 1 to 10 to the power 5, and each node's value is ranging from 0 to 10 to the power 6, and at most 10 to the power 5 calls will be made to the hasNext and the next function. And we are expected to implement the next and the hasNext to run in average of order of 1 time of complexity and use order of h space complexity, where h is the height of the tree. Let's look at the approach to solve this problem. So we are given this input, which is the sequence of operation and their corresponding input. Okay, and this is an expected output. So the first operation is the BST iterator, which is a constructor function. This constructor function takes the root of this binary tree. Okay. First, we have to decide what data structure we have to use in the class. So as per the problem description, we are expected to implement the next and the hasNext function that runs in order of 1 time complexity, and we are allowed to use space that is equal to the height of the tree. Okay. So to satisfy those, we can use a stacked data structure. Okay. To begin, so in the constructor function, we start from the root and try to locate the leftmost leaf node. So in this case, 3. Okay. So as we traverse until we reach the leaf node, we keep pushing the traversed nodes. In this case 7 is pushed and then 3 is pushed into the stack. So now when the constructor function is complete its execution, the stack will have all the nodes present in the path from the root all the way to the leftmost leaf node. Okay, and the leftmost leaf node will be on the top of the stack. So when we make a call to the next function, we can simply pop the top element and return. So we satisfy the order of 1 requirement. Same way the hash next, we can simply check whether there are any outstanding elements in the stack by checking its length and return in order of 1 time. Okay, and if we look at the space required for the stack, at most 2 elements needs to be stored. Okay, and in this case also when we traverse here, only the 15 and 9 needs to be stored. So the maximum space required for this tree is 2 and the height of this tree is also 2. So that requirement is also satisfied. And then when we pop the node 7, the next element to be returned is 9. So we have to make this element to be on top of the stack. So for that, whenever we pop an element from the stack as part of the next function, first we have to check whether it has the right child. Okay, if it has a right child, then push that right child into the stack, and then from that right child locate the leftmost leaf node in that subtree. So for in this case, when we pop the node 7, we see there is a right child and we have to push this onto the stack, and then we check whether it has a left child. In this case it has, so we keep traversing until we reach the leftmost leaf node in this subtree. So here only one node, so in the first iteration itself we locate the leftmost leaf node. So we push 9 on top of 15. Okay, so when the next time the next method is called, the 9 will be returned. Okay, so that is what I have returned here. So define a stack in the binary BST iterator class, and in the constructor function traverse the tree using only the left link until we reach the leftmost leaf node, and as we traverse, push the elements into the stack. Okay, and in the hash next function, check the size of the stack, and if it is greater than 0, return true, otherwise we have to return false. In the case of next function, pop the element from the stack and then check whether that a top element has the right child. If so, push that right child onto the stack. So when we pop 7, we check whether it has a right child. Yes, it is. So push the 15. And then from 15, follow the left link only and find the leftmost leaf node in that subtree. As we traverse, push all the nodes traversed into the stack, so that the leftmost element will be available at the top of the stack. Let's look at the flowchart. Input for the BST iterator constructor is the root of the binary search tree. First we initialize the iterator object. Okay, then we check whether the root node is null. If so, we simply return the iterator object with the empty stack. Otherwise, we push that root node into the stack and then just follow the left link, and repeat that process and push all the nodes traversed along that path from the root all the way to the leftmost leaf node. Okay, so all the elements will be pushed. The leftmost leaf node will be at the top, and finally when we reach that leftmost leaf node, we come out of the loop and return the iterator object. Okay, and the input for the has next procedure is the iterator object. First we initialize the return value to false. We check whether that stack present in the iterator object is empty. If it is empty, we simply return false. Otherwise we update the return value to true and return that. Next we will see the flowchart for the next method. So the input for this next method is the iterator object. First we initialize the count variable and the top variable. So the count will be initialized with the length of the stack. The top will be initialized with the top element present in the stack. Okay, so we pop that element and assign that to the top variable and update the stack size. Next thing, we have to check whether the top element has the right child. If so, push that right child into the stack and initialize the node with the left child of that top right. Okay, and then check whether if it is null. If it is null, then we simply break out of the loop. Otherwise we push that node into the stack and follow only the left link. Basically we locate the leftmost leaf node in that subtree. Okay, and then once we reach that leftmost leaf node, and finally we return the value present in the top node. Let's move on to coding. First I define the stack in the BSD iterator structure as a slice of tree node pointer. Then in the constructor function I initialize the iterator object with the empty slice of tree node. Then I write the for loop to locate the leftmost leaf node. As each node is visited, I push that node into the stack. Then I update the root variable to point to the left child. Then finally I return the iterator object. And then in the next method, first I check whether the stack has an element by calling the has next function. So if it return false, then I return -1 because -1 is not in the valid value for the node's val. Otherwise I initialize the count variable with the length of the stack. And then I retrieve the last element in that slice, which is the top of the stack. Then I adjusted the stack size. So once the top element is initialized, I check whether the top element has the right child. If so, push that right child into the stack. Then I check whether this right child has a left child. If there is a left child, then I try to locate the leftmost leaf node in that subtree using this for loop. As I traverse each node, I push that node into the stack. And finally, I return the value present in the top node. Then in the hash next function, I return the boolean value of this expression length of stack is greater than 0. So if there is an element, it will return true. Next, I am going to run the test cases. Okay, there is some compilation error. Okay, let me rerun. All the tests passed. Next, I am going to submit this program. Cool, this program is accepted. Next, I am going to do the code walkthrough with sample input. We are given this sequence of operation and those operations corresponding input. Okay, and this is an expected output. Okay, so the first operation is constructor function. Okay, so when the constructor is called, first we initialize the iterator object with the empty stack. Okay, and then start from the root node. We try to locate the leftmost leaf. Okay, as we traverse, we push that each node into the stack. Okay, so starting from 7, we push that into the stack and then follow the left link and then push the 3 into the stack, and then we reach the leftmost leaf node. Okay, then finally we return the iterator object. So when we leave, the stack has 7 and 3. 3 is on the top of the stack. So the next operation is the next method call. So the next method call check whether there is an element present in the stack, and then it pop the top element from the stack. So the top element is 3. So the top is 3 and then it is removed from the stack. So once the 3 is removed, we check whether the top node has a right child. In this case it is not, so we simply return the value in that top node, which is 3. So and then in the second call to the next method, again we pop the element from the stack, with so 7 is on the top at that time, so we remove that and assign that to the top. Next we check whether this 7 has the right child. Okay, if there is a right child, then we push that right child into the stack. So 15 is pushed into the stack, and then starting from that 15 node 15's left child, we keep traverse and locate the leftmost leaf node in that subtree. Okay, so in this case only 9 is the only element in that left subtree, so we push that into the stack. So the 9 is the leftmost element in that subtree. Okay. After that, hash next method is called. It's check whether the stack has an element or not. So in this case it has some element, so it returns true. Then again the next method is invoked, so it pops the top element, which is 9, and then it checks whether 9 has a right child. It doesn't, so we simply return the value 9. Then again hash next is called. So in this case the stack has one element, so we return true. After that, again next method is called. So 15 is the top element in the stack, so that is popped, and then we check whether 15 has a right child. In this case 20 is the right child of 50, so we push that 20 into the stack, and then we check whether that 20 has a left child. In this case it is not, so we return the top value, so only 20 is present in the stack. Then again hash next is called. So since there is one element in the stack, we return true. The next method is called. We pop the top element, which is 20, and we check whether it has the right child. It doesn't, because it is a leaf node, so return value 20. Now the stack is empty. So when the stack is empty, the hash next is called. Because there are no elements in the stack, we return false. Next, I'm going to do the time and space complexity analysis for this solution. Time complexity for this solution is order of n. So if you look at the constructor and the next method, so they both try to locate the leftmost leaf node. These for loops run with linear time complexity, and the maximum number of iterations that these for loop can perform is equal to height of the tree. So in this case it may be equal to the height of the tree. So this for loop runs with the linear time complexity, so the time complexity is order of n. The space complexity is order of h. So the maximum amount of space required for the stack is equal to the height of the tree. Okay, so if the tree is balanced, that height will be log n base 2. If the tree is skewed tree, left skewed tree, then we need space for all the n elements in the stack, which is equal to the height of the tree. So that space complexity is order of h. Thanks for watching this video. Have a great day.